Now, continuing with the floating point operations, we will be talking about multiplication, division, and rounding. I will start by explaining the floating point multiplication. Suppose you want to multiply 0.5 and minus 0.4375, both of them base 10. The first step to do is to express both the numbers in binary. The second step to do is to calculate the exponent of the product. To do so, we just add the exponent of the two numbers that we're going to multiply. In this case, we have minus 1 plus minus 2, that gives us minus 3. To get the biased value of the exponent, we just add to minus 3 plus 127. Now, we need to multiply the two numbers by doing a binary multiplication. So we have the multiplicand, which is 1000, and the multiplier, which is 1110. We start by taking the rightmost bit of the multiplier and multiply it by the multiplicand. That gives us 4 zeros. And then we add a 0 on the right and multiply the second rightmost bit of the multiplier by the multiplicand. That gives us 1 followed by 4 zeros. Then we add 2 zeros and multiply the third rightmost bit of the multiplier, which is also 1. That gives us 1 followed by 5 zeros. And at the end we also add 3 zeros on the right and multiply 1 times the multiplicand. That gives us the multiplicand. So the result of our multiplication is 111 followed by 4 zeros. In this step, we need to normalize the product, but in this case, we don't need normalization since our number is 1.11 followed by 4 zeros. Also, we can check for overflow or underflow. And if we have to deal with overflow or underflow, we already studied how to deal with them previously. And in this case, also there is no overflow or underflow since the exponent, which is minus 3, is between minus 126 and 127. Now, we need to round the result to the appropriate number of bits if needed. In this case, we assume that we only need 3 bits after the decimal point. So we will get rid of the zeros at the end. That gives us 1.110 base 2 times 2 to the power minus 3. The last step is to fix the sign of the product. If the original operands have the same signs, the sign of the product will be positive. And if they have different signs, the sign of the product will be negative. In this case, the two signs are different, so the sign of the product will be negative. Now, if you want to represent our number in floating point representation, we start by the sign, which is 1 bit, and is 1 in this case because the sign is negative. Then the exponent, which is in this case 124, since we added minus 3 to the biased, it's 127. And then we have the fraction, which is everything after the decimal point, which is 1 followed by 21 zeros. Now we will study the floating point division, while also taking an example and doing it step by step. So we need to divide 91.34375 and 0.1445325, both of them in base 10. The first step we need to do, similarly to the multiplication, is to express both numbers in binary. In the second step, we need to subtract the exponent of the two numbers to get the new exponent. So we have 6 minus 3, that gives us 9. And to get the biased exponent, we just add 127, that gives us 136. In the third step, we need to divide the two numbers using long division. So we just divide the bigger number by the smaller one, and we continue to do so until we reach 0, 0, 0, 0. And in this case, the result we get is the result of our division, which is 1.001111. Same as the multiplication, the fourth step is to normalize the product if needed by shifting it to the right and incrementing the exponent. But in this case, also, no normalization is needed. The fifth step is to round the result to the appropriate number of bits, and also in this case, there is no need. The last step to do is to fix the sign, and it's the same procedure as in the multiplication. In this case, the signs are the same, so the result will have a positive sign. If you want to represent our result in floating point representation, we'll start with the sign, which is 0 since it's positive, the exponent expressed in binary, and is 136, the fraction, which is everything after the decimal point, which is 0, 0, 1, 1, 1, 1, followed by zeros. In sum, to perform floating point division or multiplication, there are 6 steps that needs to be done. The first step is to express the numbers in binary. The second step is to subtract or add the exponent of the two numbers to get the exponent of the result. The third step is to divide or multiply the number to get our result. And then we need to normalize the result or round it if needed. Also, we need to check if there is any underflow or overflow that needs to be dealt with. And then, at the end, we need to fix the sign of the result based on the sign of the two operands. Unlike integers, which can represent exactly every number between the smallest and the largest number, floating point numbers are normally approximations for a number they can't really represent. The reason is that an infinite variety of real numbers exists between, for example, 0 and 1, but no more than 2 to the power 53 can be represented exactly in double precision floating point. So the best thing we can do is getting the floating point representation close to the actual number using rounding that occurs when converting from a double to single precision and when converting from a floating point to an integer. We will be using 3 bits of precision to round to the proper value: the guard G, the round R, and the sticky bits S. Now, this is the mantissa format with the extra bits. We notice that the 3 last bits are G, R, S. In fact, when a mantissa is shifted to align the radix points, the bits that fall off the least significant end of the mantissa will go into the extra bits, which are G, R, and S. But what are exactly G, R, and S? G and R are the extra bits of precision that we use in calculations. The sticky bit is an indication of what is or could be in lesser significant bits that are not kept. So, if a value of 1 is shifted into the sticky bit, the value of the sticky bit remains 1. It doesn't change to 0 even if there's a 0 in the sticky bit at the moment. This table summarizes all of the actions that should be taken for every different value of G, R, and S. So, if G is equal to 0, we don't care what are the values of R and S, we do nothing, we don't round up or down. If you get 1, 0, 0, we round up if the bit before G is in the mantissa is 1, and else we round down. If you get 1, 0, 1, 1, 1, 0, or 1, 1, 1, we round up. IEEE also introduced 4 modes of rounding. The first one is rounding towards 0, also known as truncation. We figure out how many bits are available, and we take that much of bit and throw away the rest. For example, for the decimal 0.7783, if there are only 3 places for decimal available, we throw away the 3. If 2 decimal places available, we throw away 8 and 3, and etc. The second mode of rounding is rounding toward positive infinity, regardless of the value. For example, 1.23 rounding to the nearest positive infinity is 1.3, and similarly minus 2.86 is minus 2.8. The third mode is rounding toward negative infinity, also regardless of the value. For example, 1.23 is rounded to 1.2, and minus 2.86 is rounded to minus 2.9. The last mode of rounding is rounding to the nearest even. For example, 3.5 is rounded to 4, but 2.5 could be rounded to 2 or 3, depending on the sticky bit. If the sticky bit is equal to 0, we round it to 2, and if it's equal to 1, we round it to 3.